Hi, my name is Antje. I work as a developer advocate for AI and machine learning at AWS. Thanks for joining my session, Building NLP Models with Amazon SageMaker. Let's have a quick look at the agenda for this session. First, I'm going to show you a quick introduction to NLP. We're going to talk about the popular algorithms and concepts. And then I'm going to dive a little bit more into the BERT family of models. And then I show you how to build NLP on Amazon SageMaker, featuring Tensorflow, PyTorch, and Apache Maxnet. And of course, we will have a demo. So let's get started. Let's have a look at natural language processing. NLP is a major field in artificial intelligence, and it has been studied for a long time already. In NLP, the applications require a so-called language model in order to predict the next words. The language model consists of vocabularies which can be hundreds of thousands of words across millions of documents. So the problem we're facing here is, how can we build a compact mathematical representation of the human language that will help us with a variety of NLP tasks we want to perform? And as I said, it has been studied for a long time. So if we look back to 1957, an English linguist called Firth coined the term, "You shall know a word by the company it keeps." And it's still relevant nowadays. So if you think of how machines communicate, they're not using language, human language, words. So machines need numbers. So what we have to do is basically take our words and encode them in vectors, also called word embeddings. And they can get high dimensional, at least 50, sometimes up to 300 dimensions. Having words encoded in vectors gives us a couple of features. We can encode semantics, so we can find words with similar meanings because they should have similar vectors. For example, car should have a similar vector as automobile or sedan. Also, working with vectors, we can calculate distances. So the distance between Paris and France should actually be similar to the distance between Berlin, guess what, and Germany. Also, the distance between hot and hotter should be similar to the distance between cold and colder. So we're really kind of able to encode semantic now with those word embeddings. So at a high level, what are the steps needed in NLP? We always start from a large text corpus. That could be hundreds of millions of words, billions. And the popular one is definitely Wikipedia or a collection of books, which you can use to train your model. We then need to pre-process the corpus into tokens. And tokens can be single words or multi-word entities. We then build the vocabulary from those tokens and learn those vector representations. And if that sounds like a long and heavy process, it definitely is. But the good news is that you don't have to do that from scratch every time. You can actually leverage pre-trained models that have already those existing vector representations. And we're going to see more about this later. I mentioned language modeling, but there are many more popular NLP use cases. For example, machine language translation, representation learning, text classification, sentiment analysis, you name it. NLP has really reached almost every industry and a variety of use cases. Let's have a closer look at the popular algorithms and concepts and a little bit of the NLP history. And if you see the history here, it's really all about the last couple of years. So in January 2013, Word2Vec got released. And Word2Vec uses a shallow neural network and the concept of continuous bag of words and continuous skipgram. And those two concepts work either by predicting the current word and looking at the context of words surrounding, or taking the surrounding context words to predict the current word. Then in 2014, GloVe got released. GloVe stands for Global Vectors for Word Representations. And here the change is that GloVe actually uses matrix factorization instead of the neural network to get to those word embeddings. Then in 2016, fast text appeared. And fast text, you can think of an extension of word2vec. The difference here is that each word is treated as a set of subwords called character engrams. But looking at those algorithms, they all have some limitations. For example, words have different meaning. So I could say, Kevin, stop throwing rocks, and machine learning rocks. And obviously the word rocks has completely different meaning in those sentences. But in word2vec and those algorithms, they would encode the different meaning as the same vector. Also, another limitation is that the bidirectional context is not taken into account. Meaning, if you're reading a sentence left to right, meaning you know the previous words, and reading the sentence right to left, meaning you know the next words, this is kind of building up this bidirectional context. And those algorithms don't have that visibility. So they're either reading from left to right or from right to left, but not both at the same time. So this opened up actually the research space for a lot of more different approaches and architectures how to implement NLP. So in 2018, ELMO got released. ELMO stands for Embeddings from Language Models. And in ELMO, we're implementing recurrent neural networks, LSTMs, to get to this context. And the way it implements is by executing two unidirectional LSTMs. So in a forward pass, we're first reading from left to right, and then in a backward pass, we're reading from right to left, and we're concatenating those two. And this is actually why I called it pseudo bidirectional on this slide, because it's kind of learning that bidirectional context into different model architectures. A couple of months earlier, in 2017, a paper got released called Attention is All You Need. And in this paper, they introduced a new mechanism called self-attention, and also a new architecture based on transformer. And this basically led to the introduction of BERT then in late 2018. BERT picked up a lot of those concepts in its implementation. So one is it replaced the LSTMs with those transformer architectures and also implemented a true bidirectional attention. And if you're now wondering how attention looks like, have a look. If we're giving the sentence, this movie is funny, it is great. Applying attention means we're able to detect the key words. And we can also say, picking here on the id, which is the word it actually refers to. So this one obviously refers to movie, right? The movie is great. So it got picked up correctly by this self-attention mechanism. And this is true bidirectional attention and context awareness. So let's move on to the BERT family of models that basically picked up that concept and implemented it. BERT stands for bidirectional encoder representations from transformers. And as I just said, BERT improves on ELMO by replacing the LSTMs with those transformer architectures, which are basically also better in dealing with the long-term dependencies found in text. It's also implementing this truly bidirectional architecture, left to right and right to left, in the same network. So also different from Elmo, where it's like 2 passes, BERT learns it in the same network. BERT also adds 2 more things in the training phase. Words are randomly masked to improve the learning, and it also pairs sentences randomly in some cases to improve next sentence predictions. And again, you don't have to pre-train your BERT models from scratch necessarily. You can also leverage ready-to-use models. 2 of them are BERT base and BERT large. And as you can see here on the slide, they mainly differ in the size, number of layers, hidden units, and obviously the parameters it got trained on. So let's have a look at what BERT does different in those steps. The first step we're doing when we build a model from scratch is the pre-training phase. And here we're taking this generic pre-training data, which could be Wikipedia, book collections, etc., whatever large-scale text corpus you have at hand. And in a supervised training step, we're then applying this masked language generation and the next sentence prediction. And I'm going to show you how they work in just the next slide. So once we're through this pre-training phase, which can take a long time, we're then doing in a supervised training step the fine-tuning. And in the fine-tuning, we're taking a domain-specific training set to teach the model, let's say, to do text classification or question answering. And if this sounds familiar to you, if you maybe have been working in computer vision and you've seen transfer learning, you're right. This is a similar concept, basically, of transfer learning in NLP. And this really kind of changed the paradigm a little bit. So the pre-training really becomes the new training, and training becomes the fine-tuning. So let's have a quick look at the masked language model. So as I said, BERT in the pre-training phase randomly masks 50% of all tokens and then tries to predict the token. So let's say we pass a sentence, the movie is great, and we're masking the token movie. We're then giving BERT this task to actually predict this token. And it's giving us the probability of whatever token it predicts. And this helps to build up an improved learning process. The second step it performs in pre-training is predicting the next sentence. So in 50% of all cases, it replaces a sentence in a sentence pair with another random sentence. And the goal here is really to learn logical coherence in your text. So let's say I have a sentence, this movie is great, I love thrillers. This is the sequence it appears. And there might be, in 50% of the time, I replace it with something like, this movie is great, tomorrow is Saturday. So we're passing those sentence pairs to BERT, and BERT predicts whether it's a pair or it's not a pair. And note that both steps, the masking of tokens and NSP, can happen or are actually happening in parallel. All right, so once we're through this pre-training, our task is really to fine-tune the model to a domain-specific exercise. So let's say we want to implement a star rating classifier. And you can think of like, if you visited Amazon.com recently because you wanted to look for a specific product, you might have visited this customer review section on the website to see if other customers like the product before you actually purchase it. And this is basically the star rating. So let's say I want to fine-tune the BERT model to give me the star rating for any given review text. So let's assume I put in, this product is great. I want to have BERT predicting this might be a 5-star rating. And to do this, this is happening in the fine-tuning step. So we're providing the model with very specific training data, in this case, the reviews data set. It is also labeled with the star categories, so the model can actually learn to do that text classification. So looking at BERT really created kind of a BERT mania in the industry since it got released. So there has been a lot of work happening since 2018. And here's just a couple of examples. In the fine-tuning, for example, pattern BERT is classifying patterns. BioBERT is trained and fine-tuned on optimizing and recognizing biomedical language. Camembert is actually a French language BERT implementation. Funny name. And there's also evolution happening in the architecture. So we will see DistillBERT in a demo here later. And DistillBERT is kind of a slimmer distilled version of BERT. All right, let's move on to NLP with Amazon SageMaker. And just as a quick recap here, Amazon SageMaker is a fully managed service that helps you build, train, and deploy models at scale and quickly. And I know this slide is a little bit of an eye chart, but over the last 12 months, we probably released more than 50 features and functionalities as part of SageMaker. And it's getting really hard to kind of put them all on a single slide anymore. So if you've missed some of them, I would highly encourage to have a look. Whether you're preparing the data, you're building your models, you're training, tuning them, or deploying and putting them in production, there have been a lot of additions in capabilities to SageMaker. Let's have a look at popular deep learning frameworks. And in AWS, it's really all about giving you the choice to pick the right tool for the right job. Having said that, we definitely see Tensorflow, PyTorch, and Maxnet among the most popular frameworks. So let's have a quick look how you can work with Tensorflow on AWS. Tensorflow is really a first-class citizen on Amazon SageMaker. We provide built-in TensorFlow containers for both training and prediction, and you can find the code available on GitHub. So you can pull the code, build the container, run it on your machine, and you can customize it in any way you want. We're also supporting a broad range of TensorFlow versions. In addition, you can leverage all of the TensorFlow tooling you want to do. You can pull in TensorBoard, you can leverage TensorFlow serving, or you can leverage any of the SageMaker built-in features. You can also choose between running TensorFlow on GPUs or CPU architectures, and obviously also to do distributed training. All right, enough slides for now. Let's actually jump to the demo. And I've put in here the link to the notebook if you want to run it after the session. So as a data set in the demo, I'm using actually the customer reviews data set. And in the example I shared before, we were seeing those customer reviews from the Amazon.com website. Amazon actually released an open data set for everyone to use. It consists of over 130 million of those customer reviews from 1995 to 2015. So it's a really cool data set if you want to use it in your NLP tasks. All right, so in the demo, we're implementing this text classification to give us the star rating for any given review text. The steps we need to do here is we need a data set of labeled sentences. And hey, we got this. Then we're grabbing a pre-trained model and add a classification layer to it. We then need, as part of a feature engineering process, to convert each sentence in that Amazon review to a list of vectors, and we're using a pre-trained BERT tokenizer to do that. Then we're training, or better said, fine-tuning the model to predict our star rating class. All right, so let's have a look. All right, I'm now in the Amazon SageMaker notebook environment. And in this notebook, I want to show you how you can do BERT fine-tuning with TensorFlow on SageMaker. So again, here's a quick recap in the beginning with the differences between pre-training and fine-tuning. What I've done in preparation is I used a pre-trained BERT model to generate the features already. So I generated the BERT embeddings from the review body text of our customer reviews dataset using this model. And what we're going to do now in this notebook is basically set up the environment to fine-tune, which means we're adding a classifier layer on top of the pre-trained model. And you can use, obviously, any framework you like. In this case, I'm using Tensorflow. And then we're going to kick off and train the classifier using the review body BERT embeddings, which I created, and the star labels. So again, to save us time, I've done the feature engineering already. So as part of that, I pulled down the data set from the Amazon bucket, and I used Amazon SageMaker processing job to generate those embeddings. I then split the data into the training, validation, and test data set. And also important to note that I stored the data in TF record file format, which is optimized for the TensorFlow training, which we're going to do in just a bit. So here again is a quick recap. The input data, again, is the star ratings as our label and the review body text. And the outcome here of this step is still the star rating, but the text now got transformed into those BERT embeddings. So now we're ready to do the fine-tuning. And to do that, I just set up my environment here. And I'm using the Hugging Faces transformer. Hugging Face is a company that specializes in natural language processing. And they're providing architectures you can use for TensorFlow and for PyTorch. So have a look. Transformers are really popular here, both available in TensorFlow and PyTorch. And this is basically what I'm using here to save us time to implement all of that. So I will use a variant of BERT called DistillBERT, which Hugging Face released, which uses and requires less memory and compute and turn out to have still very good accuracy on this data set. So I'm pulling in a couple of SDKs here to work with Amazon, so our Bodo, Python SDK, SageMaker. I'm also using Pandas later on. I'll set our environment up here, calling the SageMaker session and also getting the execution role, etc. As a first step then, as I provided some sample data here to speed this up, I upload those TF record files into S3. If you're actually running the whole end-to-end workshop from the Git repo, you would have them already in your S3 bucket. And obviously, if you're doing this processing on your own, you would have the features as well, probably already in S3. Then I'm just using this store here to pass on a couple of parameters from one notebook to the other. So either you're uploading or you have the features already in S3. And then I'm specifying basically where to find them. So I'm setting here the training data location, validation, and test data location, making sure here with the quick ls command that I'm really in the right path. So you can see here for this sample, I've just pulled two categories from the reviews, basically digital software and digital video games. Those two are smaller data sets, so actually we don't have to wait a couple of hours, but just around 15 minutes later for the training. Then another nice thing to note here is when you're distributing the data to your training instances, meaning when you're performing distributed training, you can basically set a distribution strategy, and you can either do a full replica, meaning that the whole data set gets copied to each training instance, or you can use sharded by S3 key, which I'm showing here, which basically means I'm dividing the data and each training instance gets part of it. So in our case, as we have the two input files here, the two TF record files, and if I'm doing two training instances, each instance would get one file. This makes sense, so let me actually do this here. And then we still need to run code. So in this case, I'm showing you how you can bring your own training code, which is called script mode in SageMaker. So here I've created a Python script which implements actually the BERT fine-tuning. So have a look at this script. You can see here I'm pulling in the transformers from Hugging Face, and I'm also pulling in a couple of SageMaker libraries here. I'm pulling in Tensorflow, also something called SageMaker Debugger, which you'll see in a bit. And again, from the transformers, we're using the Dilbert tokenizer. And you can see here basically how the training script is set up. So I'm going to show you also pipe mode in just a bit. So here I'm just checking if I'm using pipe mode to read the data. And basically the rest is pretty much TensorFlow code. Note that for script mode, we need to pass a couple of variables here from the environment. This is done here. And then also, obviously, we're passing in the hyperparameters. And then we're basically keep going with the training script. Use this as a reference if you like. There are also plenty more examples how you can do this, but feel free to have a look here in more detail after the session. And then once we're done with the training on our data set, I'm also doing some test runs at the end. So we're gonna pass actually 3 example reviews. So I loved it, I will recommend this, it's okay. And really bad, I hope they don't make this anymore. And actually check here in the inferencing part if our model provides us with the right star labels. All right, this seems fun. So let's switch back to the SageMaker environment. So this is, as I said, our training script. We also set the hyperparameters for this classification layer. So let's just do one epoch here. Feel free to do whatever you want if you run this later. We want to do distributed training. So I'm setting it to 2 instances. And I'm also using our GPU powered instances, the P3 family here. So I'm picking the P3 to X large, which provides NVIDIA GPUs. So we can actually have the training complete in a reasonable time. This one actually here takes roughly 15 minutes if you run it. And I just mentioned here pipe mode. So interesting, you can use file or pipe mode. And as the name suggests, if you're using file mode, the whole file gets copied over to your instance. In pipe mode, you can think of similar to Linux pipes if you're familiar with the concept, where you load data as needed. So this is basically loading the data in small batches to your instance, piping it. So we're going to use that just to optimize a little bit more. And we're also setting up an experiment. So a new functionality within SageMaker is basically the experiment tracking. So I'm going to use that. So I'm creating here my experiment for this training job. And I want to log the hyperparameters. So I'm creating a tracker object here and passing all of the hyperparameters. Again, I'm logging the 3 input locations here as well, where the data set is stored. And then within an experiment, you can obviously have many trial runs. So I'm setting up a first trial run for us. Just really kind of basic setup, giving it a name, etc. And I also want to check on the model performance. So I want to keep track of the training loss, training accuracy, etc. So I'm defining those here, and actually you have to pass those regex expressions. And then another functionality with SageMaker Debugger gives us the option to actually keep track of what's happening throughout the training run itself inside. So there's a couple of built-in rules. For example, loss not decreasing. So if you're passing that rule, we're basically checking in real time when the model loss is not decreasing anymore. So we can have that information. And we're also checking here in case we're overtraining. So let me set up these debugger rules here, create a hook, and then we're finally ready, boom, to set up our fine-tuning job. So for that, if you've worked with SageMaker before, it shouldn't be too surprising. So I'm pulling in from SageMaker TensorFlow, the TensorFlow estimator. So I'm basically creating this estimator object to be able to run our TensorFlow code. And as we're doing script mode here, the only thing I have to do, as you can see, is passing this script, which I've shown as an entry point. If you have more requirements you want to pull in, then just put your requirements txt in a source directory, which you're specifying here, and it gets picked up. Then we're basically passing all of the hyperparameters and information we set up before. Also make sure, again, here the training instance count, you're not doing more training instances than you actually have data. So we have the 2 data files, so it doesn't make much more sense than having 2 instances here with a sharded by a 3 key. So I'm going to do that. And then also I'm defining the framework version, the TensorFlow framework here. So I'm setting this to use 2.1.0, passing the hyperparameters, passing the input mode. So we're doing pipe mode here. The metrics I want to keep track of, the debugger rules, the debugger hook config, and also setting a training maximum run here of 2 hours. All right, so training the model now. It's as easy as just calling the fit then on this estimator object and giving it the path to the training, validation, and test data. We're also making sure that we set the experiment config here, so we're making sure it's part of this experiment. And with that, the training job got created on Amazon SageMaker. We're checking here again on the name. And as soon as the training is done, you can basically peek in here to the training job itself, to the CloudWatch logs, and also have a look at the S3 output data. So basically, I want to check actually if our model does some good predictions, right? So let's peek into the CloudWatch logs. And you see here the 2 instances, the 2 P3 instances that got started. So let me open up the logs from the first instance. And you can see here everything that's got set up. So everything pulled in, hyperparameters passed, data loaded, debugger rules kicking in. And I'm scrolling down here to the very end because I want to see actually how our predictions are doing. And here you can see our text that we passed. I loved it. I will recommend this to everyone. And you can see the prediction actually gave it a 5-star rating. Yes, with a score probability of 92%. So it's pretty sure I will love it. It's a 5-star rating. Perfect. The it's okay. It's said, well, give it a 3-star rating maybe. It's not so sure if there's 30%, but I think it's the right rating. So I'm actually happy with that. And then really bad, I hope they don't make this anymore, receives the label of 1. Also, again, with a pretty confident score. So yeah, our model has been fine-tuned and is actually predicting reasonable results. So great job. Feel free to poke around here. Training job takes you to the SageMaker training job site here in the console, so you can have a quick look. Note here, you only get billed for the actual seconds the model got trained. Really good. Feel free to also leverage our spot trainings. I didn't do it in here, but obviously this is a huge cost saver, so feel free to leverage that. Just make sure you're setting checkpoints in your model. And you can see here, just to double check, we trained here with 2 instances on P3 to X large instance family. All right, the rest I think is pretty straightforward here. And yeah, this concludes here the fine-tuning on BERT. You can definitely have a look here also at the experiment results. So here's code that you can just execute on your own. And basically, I'm just pulling the results here into a pandas data frame. And you can see here the trial run and the metrics that it recorded here. So the validation accuracy, for example, etc. You can also point it here to maybe in a different sorting. So I just created what I call a lineage table and basically sorted by creation time and order ascending. So obviously, if you're running more trial runs, you see more information here, but it's a nice way to keep track of your experiments. And also, if you want to peek in here to the analyze, to the debugger rules, as you remember, we put loss not decreasing as a rule. And you can see here the status, no issues found. So actually, we didn't run into a situation where we actually overtrained. Overtraining, no issues found. Perfect. So this concludes this demo. As I said, in the Git repo, you'll find a lot more notebooks here, especially if you're interested in how to prepare those bird embeddings. Have a look here at the prepare section of this notebook environment. All right, and with that, let's hop back into our slides. Next, let's see how you can work with PyTorch on AWS. PyTorch is a deep learning platform that really has become popular, not only in research, but across the industries. And we see a growth really happening in the cases PyTorch is getting used. It comes with a lot of benefits, whether it's eager and graph-based execution, its Pythonic way, how it's implemented. You can leverage dynamic neural networks. Obviously, you can do distributed training and also leverage GPU and CPU environments. If you want to use PyTorch on AWS with SageMaker, it is similar to the code example I've just shown you in the demo. Let's say you want to use script mode again to maybe train, fine-tune your BERT model, in this case with PyTorch. So this is the exact same lines of code we just saw, except here we're pulling in the PyTorch estimator and pointing it here to your PyTorch code. Also, if you want to implement now your training code in PyTorch, you can leverage the same Hugging Face libraries. Actually, Hugging Face first implemented all of those models in PyTorch and then added the TensorFlow support in a second step. So you can still see all of those transformer architectures, and then the TensorFlow options are just called with a TF before the name. So feel free to reuse those. They save you a lot of time in implementing your BERT code. Looking at PyTorch in general, it has been a little bit of a challenge to deploy models to production. And this is because of a couple of reasons. There hasn't been an official model server, and you had to write custom code to deploy and predict with the trained models. And I'm super happy to announce and introduce TorchServe. TorchServe is a PyTorch model serving library built and maintained by AWS in collaboration with Facebook, which we just released recently. You're basically starting with training your models as you're used to in PyTorch, and then you can start TorchServe model server and load your trained models. And this helps you to easily deploy your models in production at scale, either hosted on SageMaker, EC2, EKS, Kubernetes, or any other machine learning platform. It comes with a lot of features. For example, you can do multi-model serving, you can do model versioning for A/B testing. It has extensive capabilities for monitoring and logging, and basically provides you with a low latency prediction API. So if this sounds interesting to you, feel free to check it out at the link I've shared here. Next, I want to introduce you to DeepSet. DeepSet is a Berlin-based startup founded 2 years ago by Milos, Malte, and Timo, and they are part of our AWS Activate startup program. DeepSet's mission is to take the recent NLP research and convert it into enterprise products. And if you remember the example I shared earlier about Camembert, the French language bird model, DeepSet actually released the first German bird model and also added algorithms for transfer learning and question answering. We're working with DeepSet to optimize bird training on AWS and SageMaker. And their challenge has been how to train transformers in a more efficient way. So as I said earlier, the pre-training phase can really take up a lot of time, and time obviously means money. So DeepSet looked for ways to optimize the training to obviously save cost and also run the training code more efficient. There are two ways, as I said, to optimize the training. One is to accelerate the training, and two is to make the underlying training resources cheaper. So let's have a look what DeepSet accomplished in the code. To make the training faster, they're leveraging a couple of settings. First of all, they're using PyTorch distributed data parallel, which parallelizes the workload across various GPUs. And this helped them in make the training 30% faster. They're also using automatic mixed precision, which is a smart way to figure out where in your network you can use floating point 16 precision over floating point 32. This helped them in accelerating the training by 80%. And then they're also using something called lazy data loading. And this helps in combining the pre-processing and the training step. So instead of waiting for the pre-processing job to finish, with lazy data loading, they can load batches of data, pre-process, and as soon as the first batch is ready, you can then start the training immediately on that first batch of data. Then for saving cost, they also leverage Amazon SageMaker managed spot training. And here SageMaker really takes care of stopping and starting the instances. And your job is to only make sure that you implemented checkpointing of all of your objects. And by leveraging the managed spot training, DeepSet was able to save up to 70% of cost. We're looking forward to working with DeepSet even more closely. We're currently partnering actually with venture capitalists as they're in their pre-Series A funding round. And as a next step, they want to publish more algorithms on the AWS marketplace. All right, so as a last part here in this session, let's actually see how you can work with Apache Maxnet on AWS. Apache Maxnet is an Apache project, no surprise, in the incubating phase. It also got adopted by Amazon in 2016 as the deep learning framework of choice, by the way. Also, it comes with a lot of benefits. It is highly scalable, debuggable, and flexible. It actually supports a variety of languages, and it also comes with optimized libraries. If you want to run a Maxnet on AWS and in SageMaker, again, it's pretty much the same code as you've seen before. So you're creating an Maxnet estimator. You can use script mode again by pointing it to your Maxnet training script. You're training the estimator, deploying it. Looking at the toolkits, Maxnet actually provides toolkits for computer vision, for NLP, and for time series. Here is the example for the Gluon NLP toolkit, and it really comes with a comprehensive model zoo and great documentation, many tutorials and examples. If you want to give it a spin yourself, here I've included a link to a notebook that actually uses the Gluon NLP library and toolkit in combination with Amazon SageMaker Debugger to visualize bird attention, as you can see here in this little graphic. So in the notebook, we're downloading a bird model from the Gluon NLP model zoo, and then fine-tuning the model on the Stanford question answering dataset, SQUAD, which is also a popular benchmark in NLP. We then use Amazon SageMaker Debugger to monitor attentions in the bird model training in real time. So really exciting, highly recommend you give it a try yourself later. So, how can you get started now with NLP on AWS? I've included a couple of links here, including again the link to the GitHub repo, which contains the demo code I've shared earlier. So feel free to have a look at those links and to also play around with that demo code. Also, please visit the Partner Discovery Zone and get in touch with our APN machine learning competency partners. This concludes the session. I hope you enjoyed, and thank you very much for joining.